You know that specific feeling of dread? You're
Yeah.
working on something important on your computer, you click save, or you try to run a script, and then
Oh,
suddenly
yeah.
everything just stops. You get the spinning wheel, the hourglass, the application just hangs.
The universal pause of modern life. You're
Mm,
just sitting there thinking, is it thinking really hard or is it just dead?
exactly. And you start this like weird bargaining thing. Okay, I'll wait 10 seconds, 30 seconds. Should I force quit? Will I lose everything?
Mm-hmm.
It's infuriating. But, well, it turns out that specific moment isn't just a glitch or, bad software. It's actually tied to one of the most famous unsolvable problems in the history of math.
It is. It's the halting problem.
Yeah.
And strictly speaking, it's not just annoying. It is theoretically impossible to completely avoid.
Impossible is a pretty strong word. But that's where we're kicking off our deep dive today. We are looking at this fascinating new paper from Metafair, Hebrew University, and Bloomberg Research. And they asked a question that, frankly, shouldn't really make any sense. Can modern AI, specifically large language models, solve a problem that Alan Turing proved was impossible almost 90 years ago?
It's such a bold premise. We're diving into the paper, LLMs versus the halting problem. And just to set the stakes, when we say impossible in computer science, we don't mean like really, really hard.
Or we need a faster computer.
No, we mean mathematically undecidable.
Okay, so that's the first thing we really need to unpack. Because if Turing, the father of computing, said it's impossible, why are these researchers even wasting their time? What exactly is the halting problem in plain English?
So back in 1936, way before we had computers like we know them, Alan Turing proved that you cannot create one universal algorithm, a master program, that can look at any other computer program and predict with 100% certainty whether it will eventually stop or just run forever.
But why not? I mean, it seems like if you just analyzed the code, looked at the loops, you could figure it out.
You'd think so. But Turing proved it by creating this brilliant logical paradox. Imagine a program that's designed to do the exact opposite of whatever your prediction tool says.
Okay.
So if your tool says you will stop, the program says, okay, then I'll just loop forever. If the tool says you will loop, the program immediately stops.
That's a trap.
It's a trap, a self-referential trap. And because of that, a universal predictor that works for every program is just not possible. It is undecidable.
Okay, so there's no crystal ball for code. The math just says no.
Not a perfect one, no. But, and this is really the whole point of the study, just because you can't be perfect doesn't mean you can't be incredibly useful. The researchers basically asked, can the new AIs, like GPT-5 and Claude Sonnet 4.5, act as a good enough crystal ball?
Can they fake it till they make it?
Essentially, can they use intuition and pattern recognition to predict if code will crash, even if they can't mathematically prove it? And the results? Well, they're pretty uncomfortable for anyone who thinks AI is just, autocomplete on steroids.
We're talking general-purpose AI going toe-to-toe with specialized tools built for this exact thing for decades. So how did they test this? They didn't just open up a chatbot and type, hey, does this look buggy?
No, that wouldn't prove anything. They put these models into a very serious competition. They used the data set from SVComp. That's the International Competition on Software Verification.
The International Competition on Software Verification.
Yeah.
Sounds like a fun party.
It's basically the Olympics for bug hunting software. And the data set they used, it's not Hello World.
I was looking at the source material. It's 2,328 C programs, and they cover some nasty stuff. Bit-precise arithmetic, recursion, memory manipulation.
It's the kind of code designed to give human developers nightmares and to trick analysis tools. In the competition, there's a category called Termination. The goal is simple. Look at the code, give a verdict. True, it terminates. Or false, it loops forever.
But there's a big catch with the scoring, right? You can't guess.
A massive catch. The scoring is brutal. Get it right, you get a few points. Get it wrong, say a program is safe when it actually loops forever, and you get hit with a huge penalty. -16, even -32 points.
Ouch. So one wrong guess can wipe out 10 correct answers.
Exactly. It forces the tools to be conservative. And the winners are usually these specialized tools we call symbolic execution engines.
Okay, let's distinguish that. What's a symbolic execution engine? It's not an AI.
No, not like an LLM. Tools like Proton, which won the gold medal, or Automizer, which took silver. These are pure math engines. They don't read code. They convert it into logical formulas and try to solve them. They're rigid, rigorous, purpose-built.
So in one corner, you have Proton, the math genius, In the other, you have GPT-5, a chatbot that can also write poetry and plan my vacation.
And they pitted them against each other. But, and this is crucial, they gave the AI a specific strategy. They didn't use them out of the box. They used a technique called test time scaling, or TTS.
I saw that in the paper. Test time scaling with consensus voting. It sounds complicated. Is it just giving the AI more time to think?
It's more like thinking in volume. If you ask an LLM a hard question once, it might just hallucinate. So the researchers set up a system that acts like a jury.
A jury of algorithms.
Precisely. Instead of asking GPT-5 once, they had it generate 20 different predictions for the same code. Then they took a random sample of 10 of those answers.
Okay, so 10 answers on the table. How do you pick the winner?
Here's the strict part. The verdict had to be unanimous. All 10 samples had to agree. If 10 out of 10 said terminates, that's the answer. 10 out of 10 non-termination, that's the answer.
What if it was like 9-1?
Then the model returns unknown. It abstains.
That seems incredibly cautious. You're throwing away the answer if 9 out of 10 agree.
Because of that penalty, in software verification, being wrong is so expensive. It is much, much better for the AI to say, I'm not sure, than to be confidently wrong and crash a critical system. This consensus method filtered out all the noise.
Okay, let's get to the numbers. Because when I saw the chart in this study, I had to do a double take.
Yeah.
How did the generalist AI do against the gold medalist?
It was shockingly close. Using that TTS strategy, GPT-5 achieved an SVComp score of 3,520.
3,520. Okay, I have no context for that. What did the winner get?
The specialized tool, Proteo, and the gold medalist scored 3,685.
Whoa, so it's right on its heels.
It's within striking distance.
Yeah.
But here's the real headline. The silver medalist, the tool automizer, it scored 3,334.
Wait, GPT-5
Yeah.
beat the silver medalist.
Yes. If GPT-5 had been an actual participant, using this method, it would have taken second place. A general-purpose language model beat years of specialized software engineering.
It is absolutely bananas. We spend decades building these specific tools, and a chatbot just comes along and says, hold my beer.
It really challenges our assumptions. And it wasn't just GPT-5. Claude Sonnet 4.5 from Anthropic was right there, too. It scored 3,448, so it also would have beaten the silver medalist.
So the top 2 LLMs are performing at this elite level. But these are the proprietary giants. Did they test any open source models?
They did, and that gap is closing faster than people realize. They tested an open weights model called CWM Code World Model. It scored 3,129. Now, that didn't beat the top models, but it ranked just behind the specialized tool automizer. That's a huge win for open source AI.
But looking at the data, there was one model that just flopped hard. A version of GPT-4o.
Ah, yes. And this is a very important part of the study. They ran GPT-4o as a non-reasoning baseline.
Non-reasoning. What does that mean?
It means they turned off the advanced chain of thought capabilities. You know how sometimes you see the model sort of think out loud? First, I'll check this variable, then I'll look at the loop.
Right.
For this baseline, they turned that off. They just treated it like a text predictor. Read this, guess the verdict.
And how did that go?
A disaster. With consensus voting, it scored 546.
Ouch. From 3,500 down to 500.
And without consensus voting, just asking it once, it actually got a negative score. It lost more points than it earned.
That tells us something huge, doesn't it? This isn't just about the model knowing code. It's about the reasoning process.
Precisely. The ability to simulate the execution, to think through the steps, that's what separates these new models. They aren't just matching syntax. They are, in a sense, running the code in their head. The jump in score is all down to that ability to think.
But, and I feel like there is always a but, it wasn't a perfect victory.
Right.
We have to talk about the show your work problem.
The witness problem, yes.
We said that if the model says a program loops forever, it has to provide a witness.
Right.
Remind me what that is. It's not just a screenshot, right?
No, it's a rigorous proof. In SVComp, a witness is a really technical file, a graph, an automaton, that maps out the exact path the program takes to get stuck. States, transitions, line numbers. It's the difference between guessing the answer is 42 and writing out the full algebraic proof.
And this is where the LLMs stumbled.
Stumbled hard. GPT-5 and Claude were incredibly accurate. They knew that the program would crash. But when they were asked to generate that specific JSON graph to prove it, they struggled.
How bad is the struggle?
Their validity rates for the witnesses were around 40%. So more often than not, even when they knew the answer, they couldn't format the proof correctly to satisfy the rules.
Why? Is the format just too hard for them?
It's a very rigid, complex format. It requires specific node IDs, edge transitions. LLMs, for all their brilliance, can be sloppy with strict structural outputs. It's like a brilliant student who knows the answer but has messy handwriting.
So the researchers thought it was less about understanding and more about paperwork.
Exactly. So they did something clever. They introduced what they called a domain witness.
What's the difference?
Instead of that complex graph file, they just asked the LLM, okay, give me a logical formula. Under what condition does this loop happen?
Like, the program loops if the variable e is less than or equal to minus 5.
Exactly that. Just the pure logic. And when they switched to this format, the models performed much, much better.
So they do understand the logic.
They absolutely do. They get the semantics, the meaning of the code. They just get tripped up by the bureaucratic file format. It suggests the reasoning is sound, even if the reporting is messy.
That's reassuring, actually.
Yeah.
But surely there are limits. I mean, if I feed GPT-5 the entire Linux kernel, it's not going to work, is it?
Definitely not. The study found a very clear link between the length of the code and how well the models performed.
Size matters.
It does. They measured the code in tokens. As the number of tokens went up, accuracy went down.
Was it a sharp drop?
A very noticeable trend. Most of the correct predictions were on shorter snippets. Once the code got long and complex, the models either got it wrong or, thanks to consensus, just voted unknown.
And the paper said GPT-4o actually gamed the system a bit on long code.
It did. This was pretty funny. Because it was so unsure about the long code, its 10 predictions were all over the place. Some said true, some said false.
Which triggers the consensus rule.
Right. It triggers unknown. And since unknown gets you 0 points, but avoids the big penalty, it actually saved its score from tanking. It failed gracefully.
A strategic shrug. I have no idea, so I'm staying out of it.
Exactly. But this length limitation is key. These models are not ready to scan million-line repositories. They're surgical tools, not industrial scanners.
And before we get too carried away, we should circle back to the start. The halting problem is still technically unsolvable. The AI didn't actually break math, did it?
No, the laws of the universe are safe. The LLMs are not solving the halting problem in a mathematical sense. They're not providing a universal proof.
They're guessing.
They're using heuristics.
Yeah.
Highly advanced probabilistic pattern recognition. They're saying, I've seen millions of loops that look like this, and this structure usually runs forever. That's very different from a mathematical proof. It's intuition, not certainty.
But it's an intuition that's right an astonishing amount of the time.
Which makes it incredibly useful.
So big picture, what does this mean for the future of coding? Are we going to fire all the verification engineers and just have ChatGPT check our code?
No, and the paper actually suggests a very specific path forward. It's not about replacement, it's about combination. They call it a neuro-symbolic approach.
Neuro-symbolic. Break that down for me. Neuro is the AI.
Right. Neuro for the neural networks. And symbolic for the symbolic execution engines, the math tools like Proton.
So how do they work together?
Well, think about their strengths. The symbolic tools are rigorous and provable, but they can be slow and brittle. The AI is fast and intuitive, but it can't always produce that formal proof.
So you use the AI to find the bug and the tool to prove it exists?
Precisely. The AI acts as the detective. It scans the code and says, hey, I suspect an infinite loop right here under these conditions. It generates that domain witness. Then you feed that hint to the traditional tool.
And the tool validates it.
Yes. So now the tool doesn't have to search the entire universe. It just has to check the AI's hunch. The AI finds the needle in the haystack. The tool confirms it's sharp.
That sounds like a powerful team.
It is. And it applies to more than just this one problem. The paper brings up something called Rice's theorem.
Rice's theorem. Is that related?
It's a generalization of the halting problem. It says that basically any non-trivial property of a program is undecidable.
Like what?
Memory safety. Will this program ever access memory it shouldn't? That's undecidable. Will this line of code ever be reached? Also undecidable.
So if LLMs are good at the halting problem,
they're likely good at checking for security vulnerabilities, memory leaks, unreachable code. This study is just the tip of the spear for using AI as a reasoning engine for all sorts of impossible software problems.
it's amazing to think we're using a probabilistic tool, something that just guesses the next word, to solve problems that are all about absolute logic.
It really is. It bridges that gap between how humans think this just feels wrong and how computers verify this is proven wrong.
So we've gone from the spinning wheel of death to a world where AI might just stop that wheel before it even starts.
That's the dream. Safer code, fewer crashes.
Before we sign off, I just want to leave our listeners with one thought. You mentioned we're moving from a world of proof to a world of high probability intuition.
It's a real shift in how we define knowing something.
Exactly. If an AI can look at a problem that mathematics says is unsolvable and give you the right answer 99% of the time just based on what vibes and pattern matching, does it matter that it can't mathematically prove it? At what point does highly probable become good enough to run our world?
That is the question of the century. In the real world, 99% is often good enough. But in code, that 1% can still be a blue screen of death.
Something to chew on next time you're waiting for your computer to unfreeze. Thanks for listening to The Deep Dive.
See you next time.